Okay. First, thanks, Professor Zhang. And today I'm going to introduce something about domain adaptation. So, I am Jian Liang from Institute of Automation from the Chinese. And domain adaptation is typically a problem of transfer learning. So, before introduce some methods of domain adaptation, we just need to introduce what is the domain adaptation. So typically domain adaptation problem is try to address this problem here. Once you for the person detection problem here, maybe the training images are collected from one city in the summer, and you can see the blue bounding box here, and you can train a model using some neural networks models or another models. So in the real world applications, we just try to deploy this model to another city or another season, maybe the winter, and you can see the surrounding is different, maybe, and there's some snow here. And this problem is also known as domain adaptation or dataset bias or domain shift or domain transfer. Here in this slide, I just try to explain. So when the training set and the testing data are from the same data set, the performance looks quite well, right? So the building, the people, the load are well classified or simple. Maybe turn the next page. Oh yeah. So when the test set just changed to another new data set that's called San Francisco-term here, and the performance just degraded a lot. You can see the trim annotations are wrong, and the road, the car are totally wrong here. And this just inspired the research of domain adaptation. So when the training set and the testing set came from different distributions. Okay, next page. Sorry. Also, yeah. So there are many downstream applications of this machine learning problem setting. So from the in the computer vision fields like semantic segmentation or classification, or some cross modality like RGB to the depth modality. So there are many domain adaptation methods here. Okay, yeah, next page. So here is a form definition of the domain adaptation problem. So typically, we just consider the traditional definition here, and there exists a source domain, just consists of many labeled data here, like XS and YS here, also known as training data. Yeah, right. And there is another domain called target domain. So consists of many unlabeled data here, XT, also known as testing data. So when these two data distributions are mismatching, so the performance always is bad on the target data. So domain adaptation tries to infer the missing labels of the target data while using all the source data and the target data in the training procedures. This is also well known as a transductive learning setting. Right. So next page. Okay. So we can easily divide the domain adaptation methods into many categories. So if we can, based on the learning task, many focus on the computer vision fields, and there are many learning tasks like semantic segmentation and image classification, or like object detection, or pose estimation, or post ready here. And nowadays, more papers, domain adaptation papers, always focus on the image classification or semantic segmentation, and some also focus on the detection programs. Okay, next page. Okay, so based on another metrics, also called different supervision from the source domain, we can also divide the domain adaptation methods into three main categories. The first category is called data-dependent domain adaptation. So in this under this setting, so we can access the source data during the training. While for the model-based domain adaptation, also known as the white box domain adaptation, we only have the source model from the source data, from the source domain, without using the originally source data. And the finally category is called prediction-based domain adaptation, which is also knowing as the black box domain adaptation. So we don't know the parameters or the type of the source model, like the white box. We just have an interface of this model as a black box. So we only have the predictions from this interface, and using these predictions, we try to explore the knowledge between in them to a new target domain. So in the following, I will try to introduce some classical methods for these three task settings. Okay, next page. Okay, so for all of these different categories for domain adaptation, the key idea is try to align the feature representation from the source domain and representation from the target domain. And ideally, we can try to align feature from the same categories across different domains together and try to push samples from different categories from different domains far away. So first, I will introduce some classical DA methods for the data-dependent category. So maybe next page. Okay, so this work may be the most famous and popular framework in the domain adaptation field. So the main idea is shown in this figure, and we have two main goals here. And since we have the labeled source data here, right? So we can easily maximize the label classification accuracy here using the labeled data from the source domain. And here we also introduce another domain classifier. This classifier just try to maximize the domain classification accuracy. For example, we can consider the features from the source domain as class 1 and a representation from the target domain as class 2. And this classifier just is a binary classifier, try to discriminate source features and target features. So as we stated before, and we just try to align the features from the source domain and the features from the target domain together. And it is also can be seen as if we can make the prediction from the domain classifier confusing, we may have aligned the feature quite well. That to say, if the domain classifier do not know which domain the feature representation comes from, so the feature space is well aligned. So here, when optimize the feature encode here, we just try to minimize the classification accuracy. So the finally objective just consists of two terms here. The first term is the label classification accuracy, and the second term is the domain classification loss. Okay, next page. And the objective is showing here. And the first term is also known as semantic label classification. And the second and the third terms just is a binary classification loss here. And we have three parts here, the feature encoder, the classifier here, and the domain classifier here, three parts. And to optimize these parameters, we just try to minimize the objective, while to optimize the parameters from the feature encoder, we just try to maximize the objective. This also forms the min-max adversary training here. Okay, next page. Okay, so after adaptation, we can see the feature representation here. These figures are brought through the TSNE visualization, and the blue points represent the source features, while red points represent the target features. So before adaptation, the red one are confusion, and these features are not well aligned with the blue points. So after alignment, so in each classes we can find there exists some red points and to be aligned with the blue point here. And we can see this is a domain alignment. So this red one can be easily classified. Okay, next please. Okay, here is another classical method here called domain adaptation networks. So different from a previous work domain adversarial training. So this method just try to directly minimize the distribution difference between the source distribution and the target distribution. And to measure the difference, they adopt a popular metric here called maximum mean discrepancy here. And the difference between with the previous work is that they used the multi-kernel version of the MMD here. And you can see in the equalizations, there are some parameters just like the coefficient beta here. And this is parameters within the multi-kernel distribution difference matrix. Okay, so no. Okay, so just stop here. Sorry. Okay, so the main idea is still to try to minimize the distribution difference here. And if we carefully look at like this objective, we can find that this paper is also a min-max objective. So they just try to iteratively to minimize the network parameters to minimize the different distribution difference, while the coefficient beta is trying to maximize the difference. So it is also a min-max objective here. Okay, maybe next page. There is another popular method called adversary discriminative domain adaptation. So generally, these methods consist of 3 steps here. So in the first step, we just need to using the labeled source data and to try to train the source model here. And there is a feature encoder and classifier here using the cross entropy loss here. Maybe next page. In the second step, we just try to, for the new unknown target images, we try to introduce a new feature encoder called target CNN here, and try to introduce another module called the discriminator here. And like a previous work, and we just try to minimize the target CNN, the feature encoder through a configuration maximization objective here, minimize adversary M here in the right parts, while to optimize the parameters within the discriminator, we just try to minimize the binary cross entropy loss here in the left part. So once we have trained the target CNN and the discriminator here, and we can go into the third step in the next page. We can directly concave the target CNN and the source classifier to form the target model. And when the target image comes, we can easily obtain these labels here. Okay, next page. Okay, there is another popular domain adaptation methods. So different between previous domain adversary adaptation methods. So this paper doesn't introduce another domain discriminator here. They just try to use 2 different classifiers here. So when to optimize the features and try to capture the difference between different classifiers. And during the training, these 2 steps are alternatively trained, and the discrepancy between 2 classifiers are minimized and maximized in an iteratively manner. And maybe next page. And we can show the details in these pages. The first, we can simply train a model here over the source domain, right? Like the loss XS and YS here. And in the second step, we just fix the future encoder and try to maximize the classification difference between the target samples, try to detect some hard one. So in the following step, we just try to fix these two classifiers and try to update the parameters of the generator, also the future encoder, by minimize the difference. So step B and step C are iteratively optimized to achieve the final model. Okay, maybe next. Okay, so here is another domain adaptation methods. So the main idea here is very simple, but also works quite well. And unlike previous methods, which try to align the source features and the target features in a global manner, so maybe we can align class 1 from source domain with class 2 from a target domain. So the adversary loss looks quite well. However, this is not what we want. Yeah, we just want to try to align representation from different domains, but in the same category, right? So the main idea here is try to use a multilinear conditional manner, which try to capture the close covariance between the domain-specific features and the classification predictions here, like this in the equalization tool here, and we can just multiply the feature representation with predictions to form a long features. So these features can contain some semantic information here, and we can directly use this information or these features to train a binary domain discriminator to align feature representations from the same categories from different domains. Okay, next please. So further, they also introduce another entropy conditional term here, like the original one here, and they suggested that if the entropy of the samples are null, this means these certains are more be confident here, and which can be assigned with a large weight here in the domain adversary alignment term. Okay, these two terms just form the finally one. Okay, next page. So, based on this work, we just came up with our method. So, a drawback of the previous work may be that if the future representation is large and the prediction there is a multi-class classification task, and the out product of the future and the prediction may be large, and which will increase the computational cost. And we just try to find if we can directly concatenate the features and the prediction together and feed forward this representation into a domain discriminator and try to find how this method works. And next page. In the left figures, we can find that the real one is just try to concatenate the features and the predictions with a weighting norm before the predictions k here. You can find that, and when the k is nearly here, we can find that this. We can find that even these simple formulations can outperform the conditional adversary networks here. And it is also very important to determine the norm control factor here. We also try to discover how these terms, the varies around during the training procedure. And we find that in the right figures, this norm becomes very stable. So we came up with a normalization factor in the next page. Yeah, here. So we just try to introduce the automatically determine the norm factor here. And normally this the K is set to 1 here. And so the norm ratio between these two parts play a very important role. So to avoid some hyperparameters here, we just try to normalize P to have the same norm of the future representation. Right, this forms the formulation of our noun method here. And in the next page. Oh yeah, we further come up with another method called particle based noun. So this method just try to project the predictions to the future space. So a simple manner is try to use the prototype. If we can multiply the prediction with the prototype, we can easily obtain the projected presentations in the future space. So to obtain the reliable prototypes here, we just try to use the labeled source data and try to update this prototype along the training procedures. And once we can multiply the prediction with the prototypes here, we can obtain the projected futures. Then we can also concatenate the new futures with the futures generated in the new networks to form the finally representation. Okay, next page. And here we show the result of both methods with previous work. So compared with conditional adversary training methods here, and our methods, noun and pronoun, achieve very higher performance here. And using the prototypes as a projection, so pronoun obtain a much higher result than that of the noun here. Right. Okay. Next page. Yeah. Here we're going to introduce another work of our method, and this is called exteriorly target domain-oriented classifier, also known as ATOC. So the main idea is try to focus on the domain shift within the classifier. So as most domain adaptation methods focus on the future alignments, our method just try to use another manners, just try to focus on the bias within the classifiers. So we assume the domain shift always exists since the target domain have the same classifier as the source domain. So to avoid this problem, we just try to introduce another additionally classifier for the target domain specifically. Okay, so in the follow page, I will introduce how to obtain this classifier. Okay, so first we revisit a popular semi-supervised learning technique, also called pseudo-labeling here. So pseudo-labeling is very simple, but also widely used in many semi-supervised learning or self-supervised learning or other like domain adaptation. So the main idea is try to use the output prediction here, like P here, and we use argmax optimization operations to obtain the pseudo label of the unlabeled data. Once we have the pseudo label of unlabeled data, we consider the unlabeled data as the labeled data, then the cross-entropy loss can be used. And to cooperate the confidence of the different unlabeled data, we can also use the confidence of the predictions here, the P here, and as a weighting importance weighting factor between the cross-entropy loss. And this formula, the finally weighted to the labeling loss here. Okay, next week. And based on this, the pseudo labeling method framework, we just try to introduce two different non-parametric classifiers here to generated reliable pseudo labels. The first one is try to use the nearest centroid classifier. So first we can a memory bank here. So in the memory bank, we need to store the class in choice of different classes in the target domain. We can obtain the centroid like this equalization here. And then once we have the choice, right, we can easily resort to the nearest centroid classifier here to obtain the pseudo labels of the unlabeled data. Once we have the unlabeled data, we can easily use the cross entropy loss here, like the loss NC in the right, yeah. Okay, this is the first solution. So in the next page. So this page we provide another solution. It's called neighborhood aggregation. So different from the one above. So we just try also using the memory bank here, but in the memory bank we just storm. We do not storm the class in choice. We just storm the previously learned features and the predictions of all the target data. So once we have all the target data, we can use in the similarity between the features and to find its neighborhood in the memory bank. For each unlabeled target data, we can easily obtain its neighbors, and then we can aggregate the prediction of its neighbors into new predictions. And this prediction is also transferred like here. And this new formula, this new prediction is considered as the soft pseudo labels of the unlabeled target data. So once we have the pseudo labels, we can also imply the cross entropy loss here and with the class importance weight before here. Yeah. Okay. Next. Yeah. Here we also show the results of both methods here. And ATOC NA means neighborhood aggregation, while ADOC NC means nearest centroid classifier. And typically the neighborhood aggregation solution always works better than the nearest centroid classifier solution, since the memory bank stores so much information. It just stores all the features and representations of the target data, while the centroid, the memory bank just stores the class centroid. Also, we also find our methods works on some semi-supervised learning tasks, like in the right table. And we find that compared with some previously semi-supervised learning methods, our methods still obtain better results here. Okay, next page. Yeah, so as we can see, so these two of our methods, the pronoun and ADOC, so focus on different aspects of the domain adaptation task, while the pronoun just focus on the feature alignment using adversary alignment structure, while the ADOC just focus on the bias within the classifiers. We can directly combine these two methods together. In the following table, we can find that when combine these two methods together, we can obtain a much higher performance here. Okay. So as we can see here, so this many methods of domain adaptation need to require the access of source data during the training. However, nowadays people are always concerned with the data privacy, like the historic record or some personal record here. So in the domain adaptation field, we're also concerned with these issues. And some papers try to come up with a new problem settings. So in this problem settings, we they just try to use the trained model instead of the source data. And the trained model is provided to the target domain. So this is also called model-based methods. Okay. So typically, and the definition is also quite similar to the one above. And the difference lies in we only have the model here instead of the source data, right? Okay, so yeah, this paper is also published in SML. Okay, and we just among the first one to find this problem and also provide a solution for this problem. Okay. Next. Okay. So to address these issues, first we needed to try to train a source model. So the source model is just simply trained use a standard classification loss here, also known as label smoothing here, in equalization 1 here. And yeah, this is okay, next page. So once we have trained the source models, we just try to find what we can learn from these source models. So in this figure, we try to using some visualization techniques to find how these features align in the feature space. We can find that different classes always forms a different cluster in the feature space. And this also corresponds to the optimization of the cross-symmetry loss. So even we don't have the data from the source domain, using the model from the source domain, we can easily obtain the prototypes of the source features through the model. Okay, next. So this motivated the framework of our method. So to be specific, we also just try to fix the classifier here, right? And we try to fine tune the feature extractor here for the target domain. And the main challenge is how to design those functions to update the parameters in the feature encoder and to make the unseen source features aligned with the target features. Okay, next page. So in fact, we just try to minimize the following mutual information, maximization loss here, and this loss can be divided into 2 parts. And the first part is also known as entropy minimization in the up equalization, and the second term is called diversity promoting here. And these 2 terms just constitute into the information maximization loss here. And with this loss in the output of the network, we accept to learn the target features, which can generate nearly 1 hot output, and also these 1 hot vectors are different from each other. This corresponds to the diversity term here. Yeah, right. Okay, next page. And through the optimization of the information maximization loss, and we can find the target features. Yeah, in the figure A, we can find the bright one are the source features, and the shallow ones are the target features. So before any adaptations, so these features are just confused with each other. So it is hard to recognize which class it belongs to. So using when updating the parameters of the target feature encoder, we can find that the target features are closely aligned with the source features, even there are some wrong alignment here. So in the following, we try to mitigate these problems using another loss functions. Maybe next page. Yeah, right here. Also, to avoid some misalignment in the feature space, we just introduce another loss functions called self-supervised pseudo labeling. So the main idea is try to explore target specifically to obtain more reliable pseudo labels. So simply speaking, and we just implied by the k-means clustering. And once we have the predictions and the features of the targeted data, and we can obtain the target centroid here, equalization 3 here, and then we can also obtain the label assignments through the similarity to the centroid. Then we can repeat this process again and to obtain the more reliable pseudo labels. Once we have the pseudo labels, we can easily using the cross entropy loss here to try to align the target features with the source of features. Next page. Okay, so this is finally objective we optimize in this method. And the first two terms corresponds to the mutual information maximization, and the last term corresponds to the pseudo labeling. Yeah, right. So different from previous work is that, so there are three related work here, and both three works focus on some future negotiate ignore the future representation learning, just try to learn the something like shallow methods, like to learn the projection or support vector machines. So to our knowledge, this paper is the first one to try to address this model adaptation problems in the deeper learning framework. Okay, so next page. So then we also extend this the conference to Parmi extensions. So to conclude the improvements, we just try to we have three new discoveries here, and within the framework, we just additionally propose one more self-supervised objective to learn semantically meaningful representations in the target domain. Then we also propose a new structure called labeling transfer after the standard training, and which only requires a labeling predictions in the target domain. At last, we also expanded the experimental evaluation by adding more data sets to evaluate the effectiveness of our methods to more benchmarks. Okay, next. So this is how the framework of the one in the Parmi versions. So here we also incorporated another new self-supervised learning objective here. The objective try to recognize the rotation of the images. So as we can see, so for an image, we can rotate the image into different degrees, and the classifier is try to recognize which degrees so the image has been rotated. So there is a 4-class classifier here, and try to recognize the rotation degrees here, and this corresponds to the objective here, which is also another classification loss here. Okay, next page. So besides, we also develop a new structure called labeling transfer here, and the main idea is also very simple. So once we have adapted the source model to the target domain, and we have the pseudo labels of all the target data, we can use the entropy values again. So the low entropy values correspond to the labeled data, which can be highly reliable, while some higher entropy correspond to some unlabeled data. Then we can use some semi-supervised learning techniques here to further enforce the performance here. And specifically, we just apply a popularly semi-supervised framework called mix match here in the right. And we directly divide the targeted data into labeled data and unlabeled data, then apply the mix match to this problem to further enhance the adaptation performance. Okay, next page. So compared with the previous variants, and the one proposed in here is have a much higher accuracy here. For the results on the VSDA data set here, we can find that when we use the self-supervised rotation, classification loss, and the labeling transfer structurally, we can obtain a much higher classification accuracy here. Okay, so we also so there are some next page. There are some take-home messages here. So through these two methods, we can find that with only the source model provided, our method can achieve much higher or even SOTA performance. Second, and feature alignment can also be achieved implicitly with output level regularization, like entropy minimization and information maximization. So most of prior methods try to use adversary training or just distribution difference minimization to achieve the feature alignment. Right. Okay, sir. To combat the domain shift, self-supervision is also useful for the domain adaptation problems. So at last, labeling transfer, also using semi-supervised learning technique is also useful for these problems. Okay. Next. Okay. So at last, we're going to do some methods. It's actually one method of our group, and this method is also called black box domain adaptation, which try to leverage the predictions from the source model, but we don't know the parameters of the source model, right? Okay, next page. Right. As shown in this figure, we can find that unlike the methods previously introduced, so here we do not have the source models as white box models. We don't know the parameters. We also don't know the type or ResNet or VGG or another like transformer or other. We don't know these information. So all we know is that we have a predictor here, and we can query our target samples into this interface, and it will output some predictions. And all we can use is these predictions from the source predict, and this is the problem setting here. Okay, so next page. Okay, this here we show our framework here, and the main idea just to try to use these predictions as a teacher output, and we just use like a teacher-student knowledge distillation framework here. You can see the self-distillation loss here. It just behaves similarly to the knowledge distillation loss. And then join the training procedures, we also incorporate some structural regularization here. And these two parts just consist of the final objective here. And next page. Okay, here we will explain how the adaptive self-knowledge distillations works. So the equalization, so just correspond to the vanilla knowledge distillation loss. We have a model which provides the teacher predictions, and we try to learn the student model. The student model try to match the output from the teacher model. And this is the vanilla knowledge distillation term. Actually, this term is also used for labeled data. That to say, we know the ground truth labels for this data. However, in this problem here, we don't have this label data. We just have unlabeled packet data. So we do not believe the prediction from the source predictors, the P here. We just try to smoothing the predictions from the source and try to using the confidence here. And just like a label smoothing, we introduce the the so-called adaptive label smoothing technique here. We just preserve the largest confidence here and then smooth the confidence of other classes and to formulate the new teacher signal. And using this signal, we can obtain the knowledge distillation loss here. And in addition, we also apply the temporal ensampling technique, which try to ensemble the prediction from previous models and currently model to obtain a more reliable signal. Yeah, okay. Next. Besides the distillation loss in the slides above, and we also introduce some structural regularization here. So for knowledge distillation, so each data is independent with each other. So here we just try to use some regularization here to strengthen the relations between different data points. The first one is called mix. So it simply use mix-up operations here, try to obtain the new samples, and these samples will have the predictions associated with mix of their prediction. Another regularization is called information maximization. It is also the same as the one we use in the pure work. So this one just try to promote the diversity between the target domain and to avoid that some data, most of the data are classified into one large classes, and it hopes that this data lies into different classes to increase the diversity. So these two terms just combine together to act as structural regularizations. And this is the final objective of our method. And the first term is the distillation loss, and the third term and the second term and the third term is structural regularizations. Yeah, okay. Next. Okay, we also extend these methods into multi-source domain adaptation. So in multi-source domain adaptations, we are given multi-source models instead of one-source models in traditional domain adaptation problems. Yeah, and the right here we also show the pseudo code of our methods for black box domain adaptations. Okay, next. So to conclude this paper, so we find that black box domain adaptation is very appealing due to the following two aspects. The first one is it is quite safe since it doesn't access the original source data nor the source models. So it is hard to recover the source data from these models. Secondly, it is also very efficient. It doesn't assume the same models across domains. So it can learn lightweight target models from large-scale source models. Moreover, it doesn't involve any adversarial training or data generations. So this algorithm is also very efficient. Okay, next. So here we also show some results of this method. In the left figure table, and we show the results on single source domain adaptation benchmarks here. We can find that our method always achieve the best performance here. And compared with some model-based methods or some data-dependent methods, the results of our methods are also very competitive. Also, in the right figure, we also provide some results on the multi-source domain adaptation tasks. The observations are also similar, and that to say our methods have nice results. Right. Okay. Next thing. So this may be the final slides of my presentations here, and these two figures just try to show the sensitivity of our key details inside the proposed method here. And if you have any interest in this paper, you can find these details in my paper. So it's hard to explain so many details in these figures. Okay, next. Okay, so that's also thanks. And if you have any interest in domain adaptation or some related topics, you can also ask me some questions here.